Chapter 10, Section 3 is entitled Theoretical Probability. We're moving from the idea of experimental probability, where we actually tried whatever they're asking us about, to the concept of theoretical probability, which is just based on mathematical facts and figures and when things are equally likely. For instance, if we're talking about the chance of the Cubs winning the World Series, and we were talking based on the experimental probability would be based on all the past results. Well, since they haven't won it in a long, long time, it's going to be a number that's pretty close to 0. But theoretically, there's two things that could happen. Either they could win the World Series or not win the World Series. That would be a 1 out of 2 chance based on that alone. That's what theoretical probability is. There's two things that can happen here. One of them is a winner, 1 out of 2. That's all we're looking at is the mathematical facts. We don't look at anything based on evidence or experiments. It's just these are the numbers that are possible. Give a conclusion. So let's look at the definitions here. We've got the definition of equally likely, outcomes that have the same chance of occurring. Theoretical probability that we've already talked about. Here's a formal definition. It's the ratio of the number of ways the event can occur compared to the total number of equally likely outcomes. Fair, when all the outcomes of an experiment are equally likely, the experiment is said to be fair. You're going to see the words fair and equally likely thrown about a lot. If things aren't equally likely, theoretical probability kind of goes out the window. For instance, if we've got a spinner and 99% of it is red and just 1% of it is black, we can't sit there and say, well, the chance of spinning the little one is 1 out of 2 because there's 2 options and one is a winner there. Not really, because the one size color area is much bigger than the other. They're not equally likely. All right, and when they're not equally likely, they're not fair. So you're going to see those words bantered about a lot here. You're going to be looking for equally likely and fair to be able to talk about theoretical probability. If they're saying they aren't equally likely or aren't fair, you may not be doing anything with theoretical probability at all. Theoretical probability is probability based on the ratios of geometric lengths, areas, or volumes. All right, that's going to play more into the concept of what I just talked about here, where if we have different size things, then we're going to look at their geometric probability. And mutually exclusive, two events that cannot both occur in the same trial of an experiment. All right, and as we scroll down, we see one more definition there, the concept of disjoint events. Those are events that are mutually exclusive. So two events that don't have anything to do with each other, like picking a sock out of the drawer and flipping heads on a coin. Those two things don't have anything to do with each other, so they're disjoint events. And we'll see all these definitions as we proceed through the lesson here today. Again, quickly from the top, equally likely, those are outcomes that have the same chance of occurring. Theoretical probability is the ratio of the number of ways the event can occur compared to the total number of equally likely outcomes. Fair, when all the outcomes of an experiment are equally likely, the experiment is said to be fair. Geometric probability is theoretical probability based on the ratios of geometric lengths, areas, or volumes. Mutually exclusive, two events that cannot both occur in the same trial of an experiment. And disjoint events are events that are mutually exclusive. Let's go ahead and take a look at number 1 here. You have an experiment that consists of spinning this spinner once, and we're supposed to find the probability of the event. Now notice on the spinner here, all these segments here on the spinner, each sector, if we were talking about it like a circle graph, are exactly the same. If 3 was way big and all the other ones were teeny tiny, all right, this wouldn't even be a valid question. Because all these are equal size, it's not a question. So they're asking about the probability of getting a 4. Now, if we were talking about the experimental probability, what would we do? Well, we'd spin this thing, let's say 10 times, and figure out how many times we'd get a 4. And that would be my probability, the number of times I land on 4 compared to the 10. But theoretical is just based on looking at this thing, not actually trying it. Well, as you can see, there's one thing that's 4, and there's 5 total sectors. So the probability is going to be 1 out of 5. Notice they note what I talked about there in the beginning, that the spinner is fair meaning that all the sectors are of the same size, with all 5 outcomes being equally likely. Now in B, they're asking about the probability of getting an even number, so we're still going to compare to the number 5, but of course my top number in this probability is going to be different. Even numbers on here are 2 and 4, as you can see it marks here. 2 outcomes that are desired, 2 and 4, compared to that 5. So the probability there, the number of possible even numbers compared to 5, 2 out of 5. All right, let's go ahead and take a look at number 2. It says an experiment consists of rolling one fair number cube and flipping a coin, and we're supposed to find the probability of the event. So the first thing they ask us to do here is they show a sample space that has all the outcomes equally likely. The outcome of rolling a 5 and flipping heads can be written as the ordered pair 5, H, meaning there's 12 possible outcomes here. All right, now what you might usually do here is do this with a factor tree. Okay? If we're talking about rolling a number cube first, well, if I roll that die on the first roll, I can get 1, 2, 3, 4, 5, or 6. And then after I roll that number cube, I'm going to flip a coin. Well, doesn't matter what I land on, the first with rolling the die, but when I flip the coin, I know I can get heads or tails, no matter what. So after I get 1, I can get heads or tails. After 2, I can get heads or tails. After 3, I can get heads or tails. After 4, I can get heads or tails. After 5, I can get heads or tails. And after 6, I can get heads or tails. So as you can see, this diagram that you see in the box here is exactly the same as this. It's just written a little differently. Here's 1 in heads, 1 in tails, 2 in heads, 2 in tails, 3 in heads, 3 in tails, on down the chart. That's exactly what this shows. It's just in a list form. All right, so that's all the equally likely outcomes there. All right, and then they're talking about the outcome of rolling a 5 and flipping heads. All right, well, as you can see here, when we look at the table, all right, there's 12 possibilities there, 12 in the list, and only 1 that says 5 in heads. So the probability there is going to be 1 compared to 12. Okay, let's keep scrolling down here. See what else they're going to have us do. Question number 3. They're asking us to find the probability that a point chosen randomly inside the circle is within the shaded region. And then we're supposed to round to the nearest 100. All right, so they're asking us here, what's the possibility that, when I just put my finger on this guy, that it's somewhere here in this dark shaded area. Okay? So here, to find what's in this dark shaded area, all right, we're going to compare the area of the circle and take away the area of the triangle. Well, the area of the circle would be this whole thing, and if I take away the area of the triangle, that's me taking out this white area. Well, that makes sense because remember, we've talked about probability as the number of winners compared to the total number of possibilities. Well, winner would be landing in this dark area. So if I find the area of this whole area and then subtract this triangle, that's going to leave me this shaded area that I want, which is the winners. We're going to compare that to the total area, which is the area of the circle. All right, so let's go ahead and find some areas here. All right, as you can see, the triangle is marked with a height of 3. And I know that this is what I need because here's my right angle. Remember, what we need when we're finding the area of a triangle is its base and its height. Well, if I've got the height, what I'm missing is the base, which is going to be this length here. But realize what that base is. All right, from here to here it's a radius, and here to here it's a radius. Well, I know from looking at this little segment here that I do have the radius number marked at 3. It just happens to be 2 radii put together. So the base there is going to be 3 and 3, or in other words, 6. Now, as you can see over here, they've got the area of a triangle formula written down as half times its base times its height. So that's going to be half of 3 times 6, which is what they're showing you there, and that equals 9. All right, now the other thing we needed there is the area of the circle. Area of the circle is pi r squared. Pi, of course, 3.14 when we've solved that before, times the radius number squared. Well, we know the radius is 3. Well, if I square 3, that's 9. So it's 9 times pi, or 9 times 3.14, which is 28.26. And you can see they rounded it off to 28.3. All right, so again, to find my winning areas here, I'm going to take the area of the circle and subtract off the triangle, because a win is landing somewhere in one of these little shaded spots. All right? So, as you can see, again, they're taking the circle and subtracting the triangle. So they're subtracting this 28.26 and the 9, or they rounded off to 28.3 and 9, and they got 19.3. And again, you want to compare it to all the possibilities. Well, all the possibilities is anything in the circle. So that's that 28.26, which again they rounded to 28.3. And we're going to divide those two. Notice it doesn't really change the idea of probability. Even though it's these geometry things we're using now, it doesn't change it. Winners compared to the total number of possibilities, and we're still dividing, and you can see they end up with 0.68 there as a decimal, or if you want to write it as a percent, move it twice to the right and add a percent sign, and you end up with 68%. Okay, here's question number 4. Number 4 says, suppose you are playing a game in which you roll 2 fair dice. If you roll a total of 5, you will win. If you roll a total of 2, you lose. If you roll anything else, the game continues. What is the probability that the game will end on your next roll? Okay, so let's talk about a few things here. First thing they're talking about is the word fair in the first sentence. What they mean by 2 fair dice is they aren't made in such a way that one side would be weighted such that it would always land on the bottom, or there's not one side that's somehow bigger than the other, or somehow somebody didn't scratch off a side and say that number doesn't count. Fair means there's nothing funny about them. They're perfectly acceptable, normal, standard dice. That's all they're talking about. Now, what they're talking about here in the first paragraph of the explanation is these ideas being mutually exclusive. All right? There's no way I could roll a 5 and a 2 at the same time. So we don't have to worry about anything that's a double result or anything like that. For instance, if we talked about the baseball team not losing. Well, there's a couple different ways not to lose. You can win or you can tie. Well, those would not then be, under that particular scenario, the way I phrased it, mutually exclusive. All right? But in this scenario, there's no way to roll a 5 and a 2 total at the same time. There's no number combination to make that happen. All right? I can't roll something that adds up to 5 and say it also rolls up to add up to a 2. Okay, so the event total 5 is what they're going to figure out first. All the ways you can get a 5. Well, you can roll a 1 and a 4, and a 2 and a 3, and a 3 and a 2, and a 4 and a 1. Now, you might be saying, well, wait a minute, they're kind of repeating there, aren't they? No, not really. All right? This example of 1 and 4, for instance, would be me rolling a 1 on the first die and 4 on the second die. This one over here, where it says 4 and 1, would be me rolling 4 on the first die and 1 on the second die. Of course, that's 2 different things. So, 4 ways to roll a 5 there. So the probability total there is 4 out of 36. Now, if you're saying, where did they get 36? 36 is the total number of possibilities. All right, we know where the 4 came from because we just listed out the 4. We can make a quick little factor tree here, or a branching diagram, to show possibilities. Here's my first roll, 1 through 6. When I get onto my second roll, well, after I get a 1 on the first die, I can get 1, 2, 3, 4, 5, or 6 on the second. If I roll a 2 on the first one, I can get 1, 2, 3, 4, 5, or 6 on the second. If I roll a 3 on the first one, I can get 1, 2, 3, 4, 5, or 6 on the second. If I roll a 4 on the first one, I can get 1, 2, 3, 4, 5, 6 on the second. If I roll 5 on the first one, I can get 1, 2, 3, 4, 5, 6 on the second. And if I get 6 on the first one, I can get 1, 2, 3, 4, 5, 6 on the second. So here's all your combinations. 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 2 and 1, 2 and 2, 2 and 3, on down the list. When we count up all the pairs here, all right, you end up with 36 pairs, which is where the 36 came from. Now, as far as getting a 2, all right, there's only one way to get a 2, all right, and that's 1 and 1. Now, you might be saying, well, wait a minute, why isn't there 2? Up top, there was 1 and 4 and 4 and 1. You said those were the same thing. You're right, I did say those are the same thing. But realize, if we flip it, the other way is to get a 1 and a 1. Well, that's exactly what we said right here. Whether I get 1 on the first die or 1 on the second die, it's the same thing. So only one way to get a 2 there, so there's a 1 out of 36 chance of landing on 2. So here now, the probability of the game ending is by adding up to make 5 or 2. So adding up these two probabilities that we found here, 4 out of 36 and 1 out of 36, adding them up for 5 out of 36. So 5 out of 36 ways the game ends, with either me winning or losing. All right, any other way, the game keeps getting played. Here at the bottom then, what they do is they summarize that in the explanation. Probability that the game ending being 5 out of 36, if you divide that out on a calculator, 0.139. If you change that to percent, 13.9%. All right, so let's go ahead and finish this up by looking at the check it out examples. Number 1 says an experiment consists of spinning the spinner once, and we're supposed to find the probability of getting an odd number. So that's the same spinner we saw before, 5 equal segments, so we don't have to do anything fancy with this one here. So as far as the odd numbers goes, there's 3 of them, 1, 3, and 5. So 3 winning scenarios because there's 3 odd numbers. Compared to the total number of possibilities, well, there's 5 total things on there, so 3 out of 5. And again, that's the theoretical probability. Not talking about the experimental probability. The experimental probability would be me actually sitting there and spinning. All right, an experiment consists of flipping 2 coins. Find the probability of getting a head and a tail. Well, as you can see, they've got an answer. Let's come up with a little tree diagram, a branching diagram to match it. All right, on the first coin flip, all right, with the first coin, I can land heads or I can land tails. When I go to flip coin 2, doesn't matter what I got the first time, I can still land heads or tails or heads or tails. So as you can see, there's 4 total possibilities there. Heads and heads, heads and tails, tails and heads, tails and tails. They're asking me to find the probability of getting 1 head and 1 tail. Well, as you can see, here's a head and a tail. Here's a head and a tail. 2 ways to make it happen out of 4 total possibilities. 2 out of 4. 2 out of 4 is a reducible fraction. It reduces down to 1/2. So the probability of getting, theoretically, a head and a tail is 1 out of 2.